Hello, today we're going to talk about monoclonal antibodies, and I'm going to make this quite relevant because at the moment I'm sitting in my spare room and we're in lockdown and isolation, and so this is a topic that is going to overlap quite a lot with what's going on currently, and I'm sure in 20 years time it'll still be relevant because we'll be talking about the history curriculum. Um, so here I've got a bottle opener from Germany, but today this humble bottle opener is going to play the role of COVID-19 virus. Okay, and what we've learnt so far is that white blood cells, when they come across a virus, they will notice the virus by its distinguishing features. We call them antigens. Yeah, they're antigens. Now the antigens are things that are on the surface membrane or the surface coating in the case of a virus, or the surface membrane of a pathogen like a bacteria, and they identify it as not self, as in a foreign invader. So if we look at this analogy, one of the things that we could say, well, we could say that this bottle top opening bit here, around here, this whole bit, we could say this bit is a massive antigen, and we would be, okay, so when we see something coming along with this, then this is COVID-19, this is the virus, and we're going to attack it, we're going to destroy it. That's all very, that might be true, might be useful, but there's also other things it could be, like we've got this kind of bumpy edge to things, we've got this bumpy edge here. So in this simplified model, we have two possible antigens. We could also look right, or we could say, well, it has a picture of Munich Cathedral on it, okay, or it has the colours of the German flag, or whatever we use as our model. It has these specific aspects to it that make it the virus we're looking for. But the problem we have is that some of these antigens are not just for this virus. Some of these things might be shared with similar things. So here comes along another pathogen. Okay, in this case it's different in most ways, but it still has a bottle opener function here. It still has this function in here. So maybe the antigens and the antibodies that arise from this antigen would also attack this. This is what happens sometimes in autoimmune diseases. So if someone has type 1 diabetes, the leading evidence is that the antibodies that attack that were created by the body fighting off another infection, a completely different infection, maybe like a cold or a flu virus that has an antigen that is very similar to some of the cell surface membrane proteins on the cells of the pancreas, so it causes them to be disrupted. So maybe these are two completely different things, but the antigen here is the same, so the body will attack both of them. This could be something we want in our body, for example. That would not be a good result. And then what about if another thing comes along that has some similarities, but in a different way? So what if this is, our common cold? This has that kind of bumpy edge that we were looking at before. So these two things will probably stimulate the same immune response, and those two things will stimulate the same immune response. So we have a problem here, and the problem is that from one pathogen, our white blood cells will create a range of antibodies, and those antibodies will work on different antigens, and that's okay in terms of fighting off this particular virus, but it also may cause complications with other situations. It's a real big problem if we're trying to use antibodies diagnostically. So you may have heard that they're trying to create an antibody test, and they're trying to create a simple pinprick test that would let you know that if you had been infected with COVID-19. Now, this poses the question, which antibodies do you use? Because if this is the common cold and this is something in your body, if you choose this antigen that antibodies are created to this antigen, then it's going to be triggered positive every single time. Everyone in the, let's say this is like a cell in the pancreas, that's the example we gave, then everyone will get that, and they'll be like, oh, the whole country's had COVID-19. Or if this is like a common cold and we use this part, then if you've had that version of the common cold, then you will think you have COVID-19, but you haven't had it, you've just had this instead. So we have this problem when we're choosing what antibodies to use in our antibody test, that we've got to make sure we choose the right one, and that's why it takes some time to get it right, because we have to look at all the antibodies that are coming out from people that have survived from COVID-19 and look at them compared to other people that have definitely not had it, and look for the key antibodies that are different between the two so that we can design an effective test. So how do these tests work then? Well, they use a thing called monoclonal antibodies. Mono meaning one, clonal meaning from a clone. So all the antibodies come from one clone. This means that they are all identical. They are all completely the same. So whereas before, when we had our pathogen here that was going to stimulate its immune response, it's going to create a variety of antigens, we just choose one of the antibodies that's created from that. We need a factory though to make these antibodies, and we could infect people, I suppose. That's something that might be morally the right thing to do because we're the ones that are taking value from this technology, but we don't. We tend to choose mice. Okay, so here's my attempt at drawing a mouse. Here we go. Here's my little mouse with his whiskers. So we've got a mouse. And what we do is we therefore put in there the antigen we're looking for. Now this technology is not just used to look for pathogens that have been invaded. In fact, this antigen could be a human hormone, like in pregnancy tests. That's what they do. They expose the mouse to human hormones and generate antibodies to that hormone that they can then use to be put into pregnancy tests. So what this mouse is going to do is it's going to have this antigen in its body. It's going to fight its infection, for want of a better word. It may not even make it ill, but it's going to generate a load of white blood cells. Okay, so white blood cells, and these blood cells are all producing a huge range of different types of antibodies of all sorts of different versions. I'm just trying to make the, there we go, all sorts of different versions of antibodies. Antibodies have a Y-shaped function in general, so I'm trying to show them as Y-shaped. And then what we do is we pick one of them. Okay, we pick one antibody that we want to clone and make lots and lots and lots of. So let's just say we take the simple one. We're going to take the Y antibody. So this is the cell that we're really interested in here, this white blood cell. But the problem is this white blood cell is going to die eventually. If we take it out of the body, it's not going to just keep producing antibodies forever and ever and ever. We need to create an immortal cell line, a cell line that will continue to divide and grow no matter what happens around it. And fortunately for us, tumours have this property. So cancerous tumours or non-malignant tumours have this ability to keep growing and dividing and growing and dividing and growing and dividing. So over here I have a tumour cell. I'm going to put a link in the description for the story of Henrietta Lacks, okay, who her cells have been used as an immortal cell line for a long time. Probably should give these cells nuclei. Here we go. And now here's our tumour cell. What we do is we're going to take our cell and we're going to fuse them together. So these two cells get fused together. Our white blood cell that produces our antibodies and our tumour cell, and it creates a new cell that can produce antibodies. And that cell is called a hybridoma. Hybrid because it's a mix of two. Okay, so it's a hybridoma cell. And this is going to start chucking out tons and tons and tons and tons and tons of identical antibodies. And all we have to do then is make sure we've got more hybridoma cells. So these cells need to divide and divide and divide, and you'll get lots and lots and lots and lots and lots of cells. Here's all my hybridoma cells, and they're going to chuck out lots and lots and lots and lots and lots and lots and lots of antibodies. And then all we have to do is separate them out, and we have our supply. Here we go, let's put it in a jar. Our supply of the antibody that we wanted in essentially infinite amounts. It's quite a simple process, but it's a very powerful process. Like we said, it's used in pregnancy testing. It will be used in a similar function in all the antibody testing that is going to go on when we come up with an antibody test for COVID-19, which at today's date we don't currently have. Okay, please check on the link and check out the story of the HeLa cells, the Henrietta Lacks cells, because that's a fascinating thing. And remember that this is all to do with finding identical antibodies that we can use to do targeted drug therapy or diagnostic testing. Take care.